So I was going to completely change tack and start talking about qubits using coins. So here's the big idea. I'm doing the same sort of thing. Can everybody hear me all right? All right. Same sort of thing. I'm replacing quantum superposition with ignorance. Rather than spinning coins or anything, the idea is the teachers and students beforehand will make these handy dandy obscuring sleeves. They're specifically made to be interchangeable. That's important in quantum mechanics. You can't tell which is the front or the back. And the point of this is to teach the students about quantum teleportation, which is a quantum communication protocol. The idea is if you want to get a qubit from place to place, the best way to do that is using light, and the world record for getting a qubit from place to place is around 100 kilometers. Some people get up to 200, that sort of thing. But that is not the distance at which you can safely send it. That's the distance at which you can detect that you're even trying to send it. So if you are doing like distributed quantum computing and you need to get 100 qubits from here to there, it just absolutely is not going to happen. You need to have a perfectly clean channel. You need to be able to get qubits from place to place without physically transporting them. So that's where quantum teleportation comes in. The idea is you begin with a couple of coins. I'm going to do tails and see if I can get this. Here we go. Tails and tails again. So right now, these two are both tails. I'm going to hook them up with my patent pending correlative inducer. Toss it in the air, and now I have no idea what these coins are, but I know they're the same, so they're correlated. So here's the idea. If you ever measure a qubit, it stops being a qubit, it becomes a regular bit. You've destroyed the quantum superposition. So instead, what I'm going to do is I'm going to teleport this coin, which is heads. You probably can't see this very well. It's heads. And the way I'm going to do it is I'm going to take this heads, I'm going to put it in the sleeve with this other one. I'm going to destroy the original heads information. I'm also going to completely start over. Good news, this was also heads. I'm going to carefully put it inside of this sleeve. Flip it together. Got a good grip on that this time. All right, now what I'm going to do is I'm going to pour the coins out of the sleeve. Since I've randomized it, there's no way to tell what the original state of the coin was. What I'm going to see instead is, there we go. What I've got is a heads and a tails. So what I know is the original coin that I wanted to teleport is different from the coins that are in these two. All I'm doing is a same versus different measurement. I'm not measuring the coin, I'm measuring the relationship of it with the guy in here. Because they're different, I'll flip this one over. Now, the state of the original coin has been teleported into this one over here. And it is in fact a heads. The coin never actually traveled from one to the other, but the state of the coin did teleport from one to the other. Isn't that cute? So, in the actual activity, the students will do this like 5 or 6 times, enough for them to get bored, but also for them to establish that the system works. The beauty of this, so the big idea is if you were to try to send your bespoke precious qubit from place to place, it'll almost certainly be destroyed. But you can send a whole bunch of these correlated packets from place to place, and even if you lose 90% of them, that last couple of bits those last that survive, you can now use them to perfectly teleport. So you can get over that whole quantum noise hump. That one's fused. There we go. You can also, let me set this up again. Heads in here. Heads in here. Correlated. Heads in here. Heads in here. And correlated. So you can also, once you have this set up, you can also do quantum repeaters. But here's how that works. I've got the blue ones are the same. Sorry, the blue ones are the same. The red ones are the same. If these two are different, then these two are different. If these two are the same, then these two are the same. So what a quantum computer, what a quantum repeater does is you can take these guys and very carefully pour one coin into the other. So my earbuds just told me they're not working anymore, so I'm gonna try to switch the audio and pray that it works.
Awesome. Things are working well. So I now have both of the coins in here, same exact process. Flip them in the air, and I get double tails. Now, since I threw them in the air, double tails is exactly the same as double heads. I'm not measuring the state of the coin. I'm comparing the two coins. So I'm never actually finding out if it's heads or tails. I'm never actually collapsing the state. I'm just doing a comparative measurement. Since the two guys that were in here are the same, these guys are the same, and they're correlated. Now, if I want to, I can do a chain teleportation, and I can once again, let's make this one tails this time. As you use the sleeves, they open up a little bit and they get a little bit easier to handle. Same idea, it was tails, flip it in the air. Compare. There we go. I've got double tails. That means the coin I wanted to teleport, which turned out to be tails, is already the same as this one. And so it is teleported over, and this one is, wouldn't you know it, it's also tails. So you can chain together a whole series of these guys using these correlated pairs. Even cooler, you can create a quantum network. You can create a hub. Go. Say I want to do this. You can create a quantum network. So, yeah, I think you can see this. This hub, because it's got a correlated pair with the pink, the green, and the yellow, these two guys can communicate with each other. These two guys can communicate with each other. By doing that correlation swapping, which is stand-in for entanglement swapping, you can then connect any nodes on the hub and teleport from any node here to any other node, which is pretty clever. And even better, just to really draw a line under it, there is no distance scale at which this doesn't work. Nicole, do you happen to have the coins I sent you?
I do.
Beautiful. Just because it's hard to keep track of these things through the mail, I wrote top and bottom on them. So, do you happen to have a coin ready?
I do.
Beautiful. Do you want to teleport to me, or should I teleport to you?
Why don't you teleport to me? So you know what you're doing.
All right. Hopefully I can get into this without stabbing myself.
I'm opening the green one.
Yes, please. Make sure that don't dump the coin out. Just put it in front of you with the top side facing up.
Okay, I just need you have your handy dandy keys there. I don't. Okay, here we go. I got a pen.
All right. I will not tell anybody. By the way, just to give you a sense of how dedicated I am to the physics, I have absolutely no idea what this coin is. I did this whole thing, taped it closed, labeled it top, and mailed off one of them. Well, 3 of them, just in case. So I'm not going to say what this coin is.
Okay.
All right. It's in. I'm going to do a comparative measurement. And I get same. That means, Nicole, do not turn it over. Just
Okay.
smoothly slide it out and tell us what you got.
Okay. On the top,
Yes, please.
I got a tails. Yay! You sent information to Colorado.
I did. So this allows the students to, for example, they should be able to figure out that if they don't do that comparative measurement and then tell the other person, this guy at the far end is a completely random coin. There's nothing, it has nothing to do with the original coin. It's not until you do that comparative measurement and then tell the other person that the teleportation actually happens. So that allows you to talk about, you know, the same sort of thing that that you were talking about a minute ago. You can't use entanglement to actually communicate. You have to physically talk in order for the entanglement to actually carry information. So anyway, that's the long and the short of it.